On June 23rd, 2025, at 11 in the morning Eastern Time, more than 350 watch parties in cities across the planet went silent at the same moment, waiting on a single live stream out of Washington, D.C. No ground-based telescope has ever produced an image this large on its first public reveal. No camera this size has ever been pointed at the sky before. No observatory has ever promised to photograph the entire visible universe over and over for 10 straight years. It is not a photograph. It is the opening frame of the longest movie ever made. Stay with me, because 7 months later, buried inside that same first batch of data, this observatory found something that shouldn't be able to exist. If you're new here, this channel breaks down real space discoveries the moment the data lands. No filler, no science fiction. Subscribe if that's your thing. Let us go back to the beginning. The observatory is named for Vera Rubin, an American astronomer who spent the 1970s measuring how fast stars orbit at the edges of spiral galaxies, and kept finding the same maddening result. They were moving far too fast to be held in place by the visible matter alone. Rubin's work, along with fellow astronomer Kent Ford, produced some of the most convincing observational evidence that most of the universe's mass is invisible, what we now call dark matter, a finding built on painstaking, repeatable measurement, not speculation. It took decades for the field to fully absorb what that meant, and reasonably so, because claiming that 85% of the universe's matter is something we cannot directly see is not the kind of claim serious scientists accept lightly. The observatory that now carries her name was designed, in part, to finally settle the deeper questions her data first raised: what dark matter actually is, and how it shapes the structure of everything else. Construction on Cerro Pachon, a mountain peak in the Chilean Andes, began in 2015. At the heart of the facility sits the Simony Survey Telescope, an 8.4-meter mirror, cast at the University of Arizona's Richard F. Karras Mirror Lab back in 2007, nearly 2 decades before it would finally see first light, paired with something that had never existed before: a 3,200 megapixel digital camera, roughly the size of a small car and about twice as heavy, assembled over years at the Selassie National Accelerator Laboratory in California, and installed on the telescope in the first months of 2025. To put that resolution in human terms, capturing one of its full images on ordinary high-definition television screens would take about 400 of them lined up side by side. Each exposure covers a patch of sky 45 times larger than the full moon, gathered in 15 to 30-second bursts across 6 filters spanning the full visible spectrum into the near-infrared. Over the coming decade, this single instrument will revisit the entire southern sky roughly every 3 to 4 nights, building not a snapshot of the universe but a time-lapse of it, the kind of continuous, repeated observation that lets astronomers catch things that move, flicker, explode, or change, rather than just things that sit still and pose. That capability is the entire point, and it's worth pausing on why nothing quite like it existed before now. Building a telescope this wide, this fast, and this sensitive all at once required camera, technology, mirror casting techniques, and data processing pipelines that simply didn't exist when earlier sky surveys were designed. Older instruments faced a hard trade-off that had nothing to do with imagination and everything to do with physics and budget. A telescope built to stare deep into a single tiny patch of sky, gathering faint ancient light over long exposures, sacrifices the ability to scan wide. A telescope built to scan wide, sweeping across huge areas quickly, sacrifices the depth needed to catch faint, distant, or fast-changing objects. For decades, astronomers simply accepted that you picked one. Rubin's entire design, and the 2 decades of engineering behind it, exist specifically to break that trade-off. A mirror large enough to gather serious light, paired with a camera wide enough to cover enormous swaths of sky, revisited often enough to catch not just what's out there, but what's changing. On June 23rd, 2025, the world got to see what nearly $810 million in 2 decades of engineering had produced. The unveiling wasn't quiet. It was a formal press conference in Washington, D.C., live-streamed in English and Spanish, watched at planetariums, universities, and museums on nearly every continent. Read that again: over 350 organized watch parties for the unveiling of a telescope. The first released images included a sweeping view of the Trifid and Lagoon nebulae, stitched together from 678 individual exposures, and a separate time-lapse assembled from data the observatory had quietly gathered during its testing phase, showing more than 2,000 previously undetected asteroids drifting across the frame in a single sweep. That test phase haul was itself already staggering. In just over a month and a half of early optimization observations, before the official 10-year survey had even formally begun, Rubin's science team confirmed more than 11,000 new asteroids, 33 of them near-Earth objects, and 380 trans-Neptunian bodies drifting in the frozen outskirts of the solar system. some more than 1,000 times farther from the sun than Earth is. One of University of Washington's lead solar system scientists on the project put it bluntly afterward. What used to take astronomers years or decades to find, Rubin was now turning up in months. But numbers like that, however impressive, were never really the headline. The headline came 7 months later, when someone actually looked closely at one single object hiding inside all that noise. Here's where it gets worse, or better, depending on how you feel about the universe quietly breaking its own rules. On January 7th, 2026, at a meeting of the American Astronomical Society, a team, led by astronomer Sarah Greenstreet of Noir Lab in the University of Washington, announced they had found something in Rubin's earliest test data that, by every existing model of asteroid physics, should not be able to hold itself together. The object, designated 2025 MN45, sits in the main asteroid belt between Mars and Jupiter, measures about 710 meters across, nearly 4.5 times the length of the Empire State Building laid on its side, and completes one full rotation every 1.88 minutes. Sit with that for a second. Not 1.88 hours, not 1.88 days, 113 seconds for an object nearly half a mile wide, spinning end over end faster than most people can finish reading this sentence twice. Here is why that number is not just a curiosity, but a genuine physics problem. Most large asteroids in the main belt are what astronomers call rubble piles. Not solid rock, but loose agglomerations of boulders, gravel, and dust, held together by nothing more than their own weak mutual gravity, the debris of collisions, stitched loosely back together over billions of years. For an object built that way, there's a hard physical ceiling on how fast it can spin before it flies apart, the same way a poorly built flywheel shakes itself to pieces past a certain RPM. For a kilometer-scale rubble pile, that ceiling sits at roughly a rotation every 2.2 hours. Spin faster than that, and centrifugal force at the object's equator should overwhelm the feeble gravity holding it together, scattering its loose material into a debris field. 2025 NN45 is spinning roughly 70 times faster than that supposed limit, and it is still, demonstrably, in one piece. According to the peer-reviewed study published in the astrophysical journal Letters, Greenstreet's team calculated that to survive rotation this extreme, the asteroid would need internal, cohesive strength comparable to solid rock. Not loosely bound gravel, but something closer to a single, coherent block. Clearly, Greenstreet said at the announcement, this asteroid must be made of material that has very high strength in order to keep it in one piece as it spins so rapidly. This is not a small correction to the textbook picture. It's an asteroid actively defying the structural category most large main belt objects are assumed to belong to, caught doing it in real time by a telescope that had barely finished being switched on. And 2025 MN45 wasn't alone. Buried in that same early dataset, Greenstreet's team identified 19 total fast rotators larger than a football field, including 3 so-called ultra-fast rotators completing a full spin in under 5 minutes, and 16 super-fast rotators spinning anywhere from 13 minutes to just over 2 hours. 19 objects, all defying the same assumed structural limit, all found not over a decade of dedicated searching, but inside a single early test run of a telescope that hadn't even started its actual 10-year mission yet. The method itself is almost deceptively simple. As an asteroid tumbles, its brightness flickers, brighter when it presents more. Surface area to the telescope, dimmer when it presents less, tracing out what astronomers call a light curve. Plot that flicker precisely enough, and the pattern reveals the rotation period directly. But only if your telescope is fast enough to catch brightness changes happening on a timescale of seconds rather than hours. What most people are not seeing in the biggest camera in the world headlines is this. The camera wasn't just bigger. It was fast and wide enough, for the first time, to catch objects flickering in brightness on timescales of minutes rather than hours, revealing an entire population of anomalously rigid asteroids that older, slower surveys were structurally incapable of detecting at all. They weren't missing this population because it was rare. They were missing it because nothing built before Rubin could blink fast enough to see it. Here's where this stops being abstract. Every space agency on Earth with a planetary defense program, NASA included, following its 2022 DART mission that successfully nudged the orbit of the asteroid Dimorphos by slamming a spacecraft into it, builds its deflection math on assumptions about what an asteroid is actually made of. A kinetic impactor works by transferring momentum on collision, and how much momentum actually transfers versus how much simply gets absorbed, cratered, or scattered depends enormously on whether you're hitting a loose pile of gravel or a single coherent slab of rock. Hit a genuine rubble pile with a spacecraft, and much of the impact energy gets swallowed up, crushing and compacting loose material, changing the object's velocity only modestly. Hit something with the internal cohesion of solid rock, and that same impact can transfer momentum far more efficiently, or, depending on the geometry, risk cracking the object in unpredictable ways instead of cleanly deflecting it, model the wrong internal structure into a real deflection scenario. And the difference isn't academic. It's the difference between successfully nudging a hazardous asteroid off an Earth-crossing path and barely denting it, or worse, misjudging how it fractures under impact. 2025. MN45 itself poses no threat to Earth. It stays safely within the main belt. But it just proved that a meaningful fraction of large asteroids may be built completely differently than the rubble pile assumption baked into current defense models. And we only just found out, because the telescope capable of noticing had only just turned on. Long before any of that data reached a scientific paper, though, the observatory itself nearly didn't make it to its own unveiling, and the story of how it survived its first real crisis is one most viewers of that polished June 23rd livestream never heard. In the weeks leading up to First Look, engineers on Cerro Pachon were, in the words of one astrophysicist working the event, in the middle of a crazy month working very hard because the telescope's brand new camera, freshly installed just months earlier, had started overheating. Then, in the early hours of one night during commissioning at around 3 in the morning, the temperature inside the camera's cryoplate, the frigid internal casing that keeps the instrument's light-sensitive CCD sensors supercooled, suddenly, inexplicably, began to climb. For a camera engineered to operate near absolute stillness in temperature and pressure, this was not a minor glitch. As the cryoplate warmed, the pressure inside its sealed chamber rose along with it, and the fear wasn't cosmetic, it was structural. Materials inside the camera housing could, under rising heat and pressure, begin to outgas, releasing microscopic contaminants that might drift onto the delicate CCD sensors and never come off again. Sean McBride, a commissioning scientist working on the camera at the University of Zurich, described exactly how serious that risk was in blunt terms afterward. The probability is fairly low, but the consequence is pretty serious. This is on the top 5 list of scariest things that could happen to the camera. Not the top 10. Top 5. On a project that had already consumed 2 decades and the better part of $1 billion, with a globally publicized unveiling now just weeks away, a camera contamination event would not have been a delay. It could have been the kind of setback measured in years, not months. The team scrambled. Commissioning scientists monitored the readings in real time through the night, trying to isolate a cause with no clear culprit yet identified, running through diagnostics on an instrument so new that nobody on the mountain had a full playbook for exactly this failure mode. Every option on the table carried its own risk. Shut the camera down entirely and lose weeks of commissioning time this close to a globally publicized deadline, or leave it running and gamble that the temperature would stabilize before any contaminant actually settled onto the sensors. There was no test run to fall back on, no sister instrument to compare against. This camera was the only one of its kind on Earth, and every decision made that night was, by necessity, a first. And then, by mid-afternoon the following day, the temperature simply reversed on its own, the camera settling back into its normal operating range as quietly and mysteriously as it had drifted out of it. The clue that finally explained it wasn't found in the camera's internals at all. It was found outside. That same night, the outdoor temperature at the summit had dropped to 5 degrees Celsius, the coldest reading recorded since the camera's installation, the first real brush with a genuine Chilean winter. The unexpected environmental swing, not any internal malfunction, appeared to have triggered the anomaly. A reminder that even a machine built with 2 decades of engineering precision still has to survive first contact with an actual mountain, in actual weather, doing things the simulations hadn't fully anticipated. The camera passed its first crisis. Weeks later, it captured the images that stopped the world. Here's what is happening right now in 2026. The observatory formally transitioned into its operations phase on October 25th, 2025, and on February 24th, 2026, it crossed a milestone quietly more significant than the June unveiling. The launch of its real-time discovery alert system, which captured 800,000 transient astronomical alerts in a single night. Supernovae, flaring stars, moving asteroids, anything that changed brightness or position between exposures flagged and broadcast to astronomers worldwide within minutes rather than months. Then, on June 30th, 2026, after more than 2 decades of construction, testing, and near misses, the observatory formally began the actual 10-year legacy survey of space and time. Today, said NSF Director Brian Stone at the launch, we begin filming the greatest cosmic movie ever made. The Simone Survey Telescope is now producing a new full-resolution image roughly every 40 seconds, generating around 10 terabytes of raw data every single clear night. Enough, if you tried to store a single night's output on standard laptop hard drives, to fill more than 100 of them before sunrise, and is on pace to sweep across every visible patch of the southern sky, approximately 800 separate times over the coming decade. In the 6 weeks of pre-survey commissioning data alone, the team had already logged over 11,000 previously unknown asteroids and confirmed the fastest large object rotation ever measured. The actual 10-year survey, the one this entire machine was built for, has only just begun. And there is already a date locked onto the calendar for the next major reckoning with all of this data. Rubin's official Data Release 1, the first full formally validated catalog drawn from an entire year of continuous legacy survey observations, covering the complete southern sky rather than isolated test fields, is targeted for release by the end of June 2028, roughly 12 to 14 months after the survey's official June 2026 start. Between now and then, the observatory will keep transmitting nightly alerts and processed images to the global astronomical community on a rolling basis, but Data Release 1 is the moment the full, systematic data set, the one capable of definitively answering how many more asteroids like 2025 MN45 are quietly spinning out there in defiance of the models, finally becomes available in complete form. That data is not a projection or a hope. It is a target built directly into the observatory's operation schedule, counting down one 40-second exposure at a time. Now, the honest part, because this story doesn't actually have a clean ending yet. Scientists still don't know for certain why 2025 MN45 is built the way it is. And to their credit, nobody on the Discovery team has pretended otherwise. Greenstreet's team laid out the genuine uncertainty plainly in their published paper. One explanation is that the asteroid is a monolithic fragment, chipped directly from the dense, coherent interior of a much larger parent body that shattered catastrophically at some point in the solar system's history. Essentially, a solid shard of a bigger rock, never reduced to rubble in the first place. The competing explanation is stranger still, that some large asteroids classified as rubble piles may not all be the loose, weakly bound structures the standard model assumes, and that under the right conditions, fragmented material can compact and consolidate back into something with genuine structural cohesion, more like hardened clay than a gravel heap. Neither explanation has been confirmed. Distinguishing between them will require follow-up spectroscopy and more, detailed physical modeling that hadn't been completed as of the object's announcement. What most people are not seeing in the headlines calling this a solved mystery is that it isn't one. It's an open question, freshly discovered, sitting right at the edge of what the field currently understands about how asteroids are built. Step back from the single spinning rock for a moment, and the larger pattern here is worth sitting with. Every model in science is built from the best available evidence at the time it's constructed, and the rubble pile picture of large asteroids wasn't lazy guesswork. It was a reasonable, well-supported conclusion drawn from decades of observation with instruments that simply couldn't see fast enough, wide enough, or deep enough to catch the exceptions. What changed wasn't the asteroids. They've presumably been spinning like this for millions or billions of years, utterly indifferent to what any telescope on Earth believed about them. What changed was our capacity to notice. A bigger mirror, a faster camera, a survey cadence built for catching things that V's on human timescales instead of geological ones. That is, over and over again, the actual mechanism by which humanity's picture of the universe gets corrected. Not by proving old scientists wrong for being careless, but by building instruments precise enough to finally catch what the old instruments were structurally incapable of seeing. Vera Rubin herself spent a career gathering evidence for something invisible, using instruments that, for their era, were state-of-the-art and still nowhere near sufficient to directly observe the dark matter she inferred. The observatory built in her name is now repeating that exact pattern one level down, pointing not at the invisible scaffolding of the cosmos this time, but at ordinary rocks in our own solar system's backyard, and finding that even those hold structural secrets nobody had the tools to notice before now. Progress, in other words, rarely looks like a single triumphant answer. It looks like a bigger camera catching something spinning too fast to make sense, and an honest scientist saying, on the record, that she doesn't yet know exactly why. Think about what that means for everything Rubin hasn't looked at yet. If a single month and a half of pre-survey commissioning data, a tiny fraction of 1% of what the full 10-year survey will eventually gather, was enough to overturn part of the standard model for how large asteroids are built, it raises an obvious and slightly unsettling question. How many other quietly accepted assumptions across astronomy, built on genuinely careful work with genuinely limited older instruments, are waiting for exactly this kind of camera to catch them out? Nobody currently knows the answer. That's not a flaw in the science. That's the entire reason the telescope was built. There is a particular image from that first data release worth holding on to after all the numbers fade. A single frame of the Virgo cluster, hundreds of galaxies frozen mid-orbit in one exposure, each one itself a swirl of billions of stars, every one of those stars moving too fast for the visible matter alone to explain. The same observational riddle Vera. Rubin spent her career chasing, now sitting quietly inside a single image from a telescope carrying her name, gathered without any astronomer even asking for it specifically, just because the camera happened to be pointed that way. Somewhere in that same wash of data, unnoticed for months, sat one small, oddly shaped rock in our own asteroid belt, spinning at a rate physics says it technically shouldn't survive, waiting for someone to isolate its light curve from 100,000 other objects and realize what they were actually looking at. The universe, it turns out, does not save its strangest secrets for the farthest galaxies. Sometimes it hides them a few 100 million kilometers away, in plain sight, in a database nobody had gotten around to reading yet. So here's everything in one breath. The Vera C. Rubin Observatory, named for the astronomer who first found strong evidence for dark matter, unveiled its first images to a globally live-streamed audience on June 23, 2025, after nearly surviving a camera-threatening overheating crisis just weeks earlier. Buried in that same early test data, astronomers announced in January 2026 that they'd found 2025 MN.4P5, a 710-meter asteroid spinning once every 1.888 minutes, roughly 70 times faster than the accepted rubble pile survival limit, alongside 18 other fast rotators defying the same assumption. The observatory formally began its full 10-year legacy survey of space and time on June 30th, 2026, is now producing a new image every 40 seconds, and is targeting its first complete annual data catalog for release by the end of June 2028. And the actual physical reason 2025 MN45 can survive its own rotation, solid fragment or something stranger still forming inside supposedly loose rubble, remains, right now, a genuinely open question. If you want to be here when data release 1 actually lands, and when we find out whether 2025 MN45 has company, subscribe and turn notifications on, because I'll be covering it the moment the data does. One question before you go. If Rubin's decade-long survey turns up a genuinely hazardous asteroid built like 2025 MN45, dense, rigid, resistant to a kinetic impact, would you want NASA to test a deflection mission against it now, while it's still harmless, or wait until an actual threat forces the question? Let me know in the comments. I read every single one.